In this exercise, we will look at the eigenvalue algorithms. We have a 2D truss structure which we already used in our previous exercises. So we have the same global mass matrix and the global stiffness matrix. However, in this case, we have an additional input parameter, the tolerance, which we'll use in our iterative algorithm. We have the following eigenvalue problem with a stiffness matrix K, mass matrix M, eigenvector, and eigenvalue lambda. We can solve it iteratively using either forward iteration scheme, where we obtain the last eigenform or the largest eigenvalue, or an inverse iterative scheme, where we obtain the first eigenform or the smallest eigenvalue. So we start here by assuming some vector x for the eigenvector and just giving some initial values for it. We also assume initial eigenvalue is equal to 1, and then if we insert here x1, here 1, and we'll obtain then the right hand side. From this right hand side then we can obtain iteratively the improved eigenvector. So we start with the loop, and here we have matrix K times our eigenvector, and we have the right hand side, and that's what we have here. And from this equation we can obtain x bar at the time step n+1. Now, given x bar n+1, we again plug it in here and obtain the new value for the y bar n+1. Then we normalize or rescale our vector y bar, and then we can obtain the eigenvalue with the Rayleigh quotient. And the last thing which we do in each step is we check for the convergence whether we have to stop the iteration or not. So we check whether the relative change in rho, the absolute value of relative change in rho, is smaller than the tolerance or not. For the forward iteration, the scheme is almost the same. We also have an initial guess for x1, but here we plug it in on the left hand side, so we multiply k with x1, and then we start our loop, and again in each time step we're updating x bar, y bar, and then again using the Rayleigh quotient we obtain rho and check for the tolerance. Now let's solve for the first two steps using the inverse iteration our task with the 2D truss structure. So first of all, we have to make an initial guess for x1. We have two components, so the easiest way will be to assume that each component is equal to 1, and then multiplying x1 with mass matrix M, we obtain the right hand side there, the vector y1. Then we start our for loop with the first step. So by multiplying inverse of matrix K with y1, this is our inverted matrix K, we obtain the following vector. Now this is the vector x bar 2. We plug it in here to obtain x bar 2, and now we have to rescale our vector y. So now we've got y bar 2, x bar 2, and we can use them to obtain our rho 2 using the Rayleigh quotient. And the last thing which we do in this step is we have to the checking whether the convergence has reached. So row 2 minus row 1 over row 2. Row 1 is the initial guess for our eigenvalue. It was 1. So of course in the first step you usually you will not achieve any convergence. So we have to go to the step number 2. In the step number 2, first thing we find is x bar 3 by multiplying inverse k times y2, and vector y2 is the vector which you found in the first step. Then we plug the x bar 3 here to update the y bar 3, and we can then rescale our y vector. So now, given x bar 3, y bar 3, we can find the row 3 using the Rayleigh quotient, and then use it to check for the convergence. So plug our row 3 here, and row 2 is the row which we found in the previous step, in the first time step. So we'll get 0.0011. It's bigger than 10 to the power of minus 5. It's bigger than our tolerance, so it means we have to continue our algorithm. So these are the 2 steps, handwritten. I've done more steps on my laptop, and after 4 steps we will reach the convergence. So our value which we obtain here will be smaller than 10 to the power of minus 5. So it means the row 5 which you find in this step number 4 is our eigenvalue. So our eigenvalue will be 2.26 times 10 to the power of 6, and the corresponding eigenvector will be y5. Here it is. And now we can, given the eigenvalue, we can find the time period as 2 pi over square root of lambda, and this is the value actually which we had in our central difference video exercise. Now the same task, the same 2 steps, but using forward iteration scheme. So we start again with the initial guess for x1. We make the same initial guess, both components are 1, and obtain y1 by multiplying with, here however we multiply it with the stiffness matrix K and not mass matrix. Then we start our loop with the first step, where we obtain x2 bar, and again here we have an inverse of mass matrix and not the inverse of K matrix. So this is the inverse of our mass matrix. After multiplication we obtain the vector for x2 bar, and then plug it in here to obtain y2 bar. Here again we, instead of mass matrix M, we have K matrix, stiffness K matrix, and we obtain the y2 bar. Normalize it, and now given x2 bar, y2 bar, y1, we can obtain the value for row 2 and plug it in here in order to check our convergence. And again, row 1 is the initial guess value for the eigenvalue, which is equal to 1, and it's bigger than our tolerance, so we go to step number 2. In the step number 2, we multiply the inverse of mass matrix with the y2, the vector which we found in the previous step number 1, this one, to obtain the value for x3 bar, and then again continue the algorithm, plug it in here, update y3 bar, normalize it, and now again, given x3 bar, y3 bar, we can find the value for row 3. And the last part is checking for the convergence. Row 3 is the value which we found here. Row 2 is the value found in the previous step. So it will be 0.61. It's greater than 10 to the power of minus 5. So we continue with the algorithm. So these were the two handwritten steps. The algorithm implemented on my laptop converges after 6 steps. So the eigenvalue will be equal to row 7, will be equal to 1.37 times 10 to the power of 7. So this eigenvalue is the largest eigenvalue because we use here the forward iteration scheme, and the corresponding eigenvector will be y7, and we again can find the period by the following expression, 2 pi over square root of lambda. So, and it will be 0.0017, and the same value which was given in the previous exercise on central difference scheme.